Okay, welcome to Thinking Beyond. Before we get started tonight, I just want to remind everyone about our upcoming topics and speakers. For Thinking Beyond on March 31st, we have Kate Adamala, and she will be talking on creating a new tree of life in the lab, threats and opportunities. And then on April 28th, we have John Mitrofanus talking on unraveling the mystery of brain cell chit chat. Do they talk with light? And then for tonight's Thinking Beyond, as always, if you have any questions during the webinar, just use the Q&A feature at the bottom of your screen and we will get to those. So I will go ahead now and turn it over to our moderator for tonight, Parikh.
Thank you, Jessica. So welcome everyone to this evening's edition of Thinking Beyond. Most of you are regulars here, but to those of you who aren't, let me just introduce the series here. My name is Maulik Parikh. I'm a professor of physics at Arizona State University and at the Beyond Center for Fundamental Concepts in Science. And with me today is also Professor Paul Davies, who's the director of the Beyond Center for Fundamental Concepts in Science. And we're the regulars, but we're very happy to have a special speaker. He's my good friend, Justin Khoury. And so Justin is a professor in the Department of Physics and Astronomy at the University of Pennsylvania. His research lies at the interface of theoretical cosmology and particle physics, investigating new models of dark matter and dark energy, as well as theories of the very early universe. So he received his Ph.D. from Princeton University in 2002, followed by postdoctoral positions at Columbia University, where I am right now, and where he and I were postdocs together. And then he was at MIT. And afterwards, he was a faculty member at the Perimeter Institute for Theoretical Physics, that's in Waterloo, Canada, before finally joining the faculty at University of Pennsylvania in 2009. He's been awarded a Sloan Research Fellowship, an NSF CAREER Award, the 2017 Buchalter Cosmology Prize, and the Lindback Award for Distinguished Teaching. So we're very happy to have him here today, and we're going to be talking about a very exciting and controversial topic before the Big Bang. All right, so let me start by welcoming Justin. Oh, so the format today, by the way, is we're just going to have a conversation, and we have Paul here as well. So I'm really with a bunch of experts here. You might hear the word bunch Davies, maybe. So we're just going to have a conversation. And as always, if you have any questions that come up during the course of the talk, please enter them into the Q&A, and towards the end of the hour, we're going to get to them. Okay. So, welcome, Justin. How are you?
Good, thank you. It's a real pleasure to be with you to have this discussion.
Great. So we're going to talk about before the Big Bang. All right. Everyone thinks of the Big Bang as a moment or the thing that's created the universe. There's even a TV show named after it now. It's part of the popular lore, but it wasn't always so. So why don't we start by, maybe you could tell us what exactly is the Big Bang, and along the way, maybe we can clear up some conceptions.
I think for such an important event in the history of our universe, it has one of the most misleading names. And first, because a Big Bang suggests some explosion of some kind where matter was flying apart from each other. And it also gives the idea that this happened in some particular place in the universe. So an analogy that I like to think about to envision what is actually happening is to think about a tablecloth, a checkered tablecloth. And imagine that you're living or confined to be on this tablecloth, living, let's say, on one of the squares there. And this tablecloth is being stretched. That's the expansion of the universe. And if you think about that, then living on this tablecloth, every nearby square is moving away from you as the universe expands. And the story backwards in time, if you play this movie backwards, you would see that in the past, each of your neighboring squares was closer to you, no matter where you are on this tablecloth, until finally everybody is so squeezed together that the density of the universe literally becomes extremely high or infinite. And that would be the distance between these squares becomes very small, and that's the Big Bang. So it's happening really everywhere in space. And also the other nice thing about this simple analogy is it suggests that it's not things that are flying apart or matter that's flying apart, but rather the space itself that is expanding. And that's really the expansion of the universe.
Right. So let's just that was a lot to unpack. So let me just go over that a little bit. So first of all, the Big Bang wasn't it's not like a grenade going off somewhere. It's not like you can visit the site where it happens and take pictures or selfies over there. It really happens everywhere in space, right? So, and what you're saying is that there's a table. The universe here is represented in 2 dimensions by a tablecloth, right? Which is a checkered tablecloth, which is expanding, and you can see that. So there's no and it's an infinite tablecloth, right? It's not expanding into anything. So that's something that people often get confused about. They think if it's expanding, it must be expanding into something else. So we just have like an infinite tablecloth, and it was infinite before and it just even more. And so the actual size doesn't change, but the separation of the point.
Exactly. Yes. For this,
I'll chip in because there's a related question, and you dealt with that very well, Justin. The related question of the fading afterglow of the Big Bang, the cosmic background heat radiation. So the Big Bang was hot. That heat radiation filled all of space, and as the universe expanded, the radiation cooled, but it's still there, coming at us from every direction. And often when I give lectures, people want to say, well, surely if there was like a flash of radiation from the Big Bang, it should sweep past us and then disappear. And the whole point is that all of space is filled with this radiation. So it's like living inside a gigantic microwave oven. It's everywhere, coming at us from all sides. And it's full of clues about the very early universe. Well, about the early universe.
Well, we're going to have a lot to say about the microwave background, I'm sure. Exactly. So that's also a good example of a kind of.
But could I just say I'm the oldest one here, and I'm not as old as the Big Bang, but I am older than the term itself, because the person who gave me my first job in cosmology was Fred Hoyle, the British cosmologist. So that was in Cambridge, and Fred didn't like what we would now call the Big Bang theory, and people. He was the one who coined that term. In a radio interview, and it was a term of derision. He said, well, of course, some people think the universe just started with a Big Bang, how absurd. And the name stuck. So Fred was a proponent of what was called the steady state theory of the universe. He realized that the universe is expanding. There was no doubt about that. We've known that since the 1920s. But he felt that it is eternal, and that as the galaxies move apart, the squares on the tablecloth move apart, so new matter is continually created to fill up the gaps and make new galaxies. And then taking a sort of God's eye view of all this, nothing changes over the billions and trillions of years. It's in a steady state. And the theory really fell down because of this background heat radiation, which is discovered in the 1960s, and it's so obviously radiation from a very compressed, hot early phase. It was impossible to account for it within the steady state theory. Though Justin, when I'll finish speaking in a moment, there is a sort of curious reprise of the steady state theory in the inflationary universe scenario, in the version of it that is called eternal inflation. We'll maybe get onto that later. So Fred is sort of on the right track, but with the wrong theory.
Right. Okay. So anyway, just to hammer home this point, you're saying that at time t equals 0, all right, all these so the galaxies themselves, the rulers themselves are not expanding, right? It's only the space between them. So if I think, and then if you put coins at the intersections of this stretchy tablecloth, those themselves are not expanding. Is that right?
Yeah, I mean, that's a great point. So that's another question that's often asked. Why is it that if the universe is expanding, I'm not expanding? Well, I'm probably expanding, but not because of the universe. But the reason is very interesting. So, of course, the expansion of the universe is because of gravity, the gravitational attraction and gravitational force between galaxies. But if we think about our own galaxies, the gravitational force that is binding the galaxies together, our own galaxy is much, much stronger than the gravitational pull from the rest of the universe. And that's the reason why we don't locally expand, but it's really the space between the galaxy that is expanding.
Right. So on small scales, it doesn't really look like an expanding universe. It looks like a,
Yes.
bound system. So if you were, I think the analogy that is in this famous Misner's Thorne Wheeler book is if you put pennies at the various intersections, the size of the pennies don't change, but the spacing between the pennies change.
Yeah.
And the Big Bang is when all the pennies are on top of each other, but it's not, sorry, they're not all on top of each other. They're all infinitely close to each other, but there's still infinite number of pennies in all directions, right?
That's right.
So it's not that that the size of the universe ever becomes zero. It's always infinite.
No, exactly. Yeah.
Right.
And
So
I think, and if we get to the nature of what is that event, what is the Big Bang, really, it's really when we extrapolate this picture all the way to this beginning as t approaches zero, as you say, then we reach densities that are so high, temperatures that are so high, that at some point we simply do not trust our description of space and time in terms of Einstein's theory of general relativity. And I think that's what we would call the Big Bang. We don't know for sure exactly what took place there simply because of our inability to describe that instant.
So really what's happening is our equations are going bang in a way. That's sort of
yes, we can.
Right? We don't.
That's exactly right. Yeah, we cannot. And
so what you're describing, Justin, is a highly idealized picture in which everything comes together like in a point, which would be we call a singularity, a point of infinite density, an edge or a boundary to space-time. And in that very simplified model, the Big Bang is the origin of space and time, as well as matter and energy. And that's a point I always try to get across. And maybe that's not the correct picture, but that was for most of my career, the belief that time itself began with the Big Bang. There was no time before the Big Bang. So when people say, well, what caused the Big Bang? You couldn't really use those sorts of terms. And then when you tell people that, they feel sort of tricked, as if, oh, you clever scientists, you use words in a way that confuses us. But actually, the notion that time itself comes into being with the universe, a very ancient one. For example, Augustine of Hippo said that the world was made with time and not in time. So it's a very ancient idea that time is part of the physical universe. So if we're talking about the origin of the physical universe, it includes the origin of time. May not have been that way, but that's in the simple picture.
So I just want to clarify one thing. We're not saying that the Big Bang is a point in space-time. It's actually, it's not a point, it's not one point in space, it's everywhere in space, it's only a moment in time. So it's not, there's no space-time point, it's rather a moment in time, like 5 o'clock tomorrow. It's sort of, that's, I think, what we're saying here, right? That it's a kind of a space-like singularity in the jargon.
Yeah, but to build on Paul's point, I think to me, I always wonder how amazing it is that, Einstein's theory of general relativity, which has been so successful empirically, phenomenologically, it's one of the most beautiful, elegant theories ever invented. And yet it points very distinctly, clearly to places where its own predictions or its own descriptions is breaking down. And as to what exactly happens as we approach in the past, I'm thinking in time, right? This moment where densities become very high, the space-time curvature is becoming very high. We don't really know. And I think Paul's perspective that this may be the beginning of time or what we may describe as time, there may be some other state there that for which space and time is simply are not the right, ingredients to describe it accurately. But or as we'll discuss, without getting ahead probably of the discussion, it may be a more speculative idea that in fact it is simply a bridge between a pre-existing phase of the universe and the current one that we are experiencing.
Before we
Right.
get to that, we should mention that Stephen Hawking thought he had solved the problem of this origin of time. But the work he did with Jim Hartle, and it's too technical for us to go over the details, but he had the idea that there was no preceding epoch before the Big Bang, but there was no singularity. It was removed by the mathematical
Quantum
trick,
event,
which
yes.
we're not going to get into
Quantum.
yet. But that he had a model of the universe which was not eternal. It didn't go back forever and ever, but nor was there a first moment where time just switched on suddenly like that. So he was able to sort of have the best of both worlds. But the thing that I always plug away at for people who defend that point of view is you may not be looking for a preceding cause of the Big Bang, but you can still ask, well, why did it happen? Explain how the universe happened in that manner. And Hartle and Hawking, of course, invoked the laws of physics, quantum mechanics, general relativity, and so on. They did some fancy stuff with path integrals. Again, don't need to get into the details. So the significant thing is you've got to believe that the laws of physics transcend the universe, that they somehow exist in some platonic realm so they can explain the universe. Otherwise, you have the problem that the universe and its laws pop into being together for no particular reason. And so that's the philosophical issue that we have to deal with. But maybe we should return to the physics.
Yeah, so I'm just going to, before we move on to the sort of next set of issues, I just want to summarize for viewers what we've just discussed. The Big Bang is a moment in time, not in, where the laws of physics are breaking down, and which is perhaps maybe the earliest moment of time. It's not a particular point in space, and it's where densities are infinitely high. That's so far what we have. And it's of course very exciting because we all want to know what time is, and the idea of whether time is at a beginning or whether it was eternal is a question that we've wrestled with for millennia. All these mythologies and cosmologies had their own stories about it, and as Paul mentioned, Saint Augustine was thinking about this. He thought of, and I think he asked, what was God doing before he created heaven and earth? And he sort of jokingly said, well, he was creating hell for people who ask such questions. And so, but what's changed now is that we have a scientific method. And with the scientific method, we can sort of distinguish between these different alternate stories and see where the evidence leads us. And so even in the scientific community, we tell us a little bit about the view of the universe that and how it changed, and what was the evidence that got us to got people to sort of almost universally subscribe to the Big Bang theory. As Paul said, it was when Fred Hoyle coined the term, it was a term of derision. He said it was a girl jumping out of a cake. But up till then, so how did that go exactly?
Right. So my understanding of history indeed is that really the discovery of the cosmic microwave background, this relic radiation coming from when the universe was 400,000 years old, that I think was a watershed moment, in that now we had evidence that the universe looked vastly different in its past than what it looks like today. It was really radiation in thermal equilibrium, no galaxies to speak of, and very different states. So at least I think that really cemented the idea that there was an evolution to the universe. The Big Bang itself, I think people had been aware of this primeval atom, I think Lemaitre called it, that, extrapolating this cosmological model that Einstein had proposed would lead you to a universe of zero size, essentially. But Paul may correct me, but my understanding is that people thought probably even after the discovery of the microwave background that this notion of a Big Bang may have been an artifact of assuming that the universe was very symmetric. It was isotropic, looked the same in all directions, and homogeneous. And indeed, I think it was Stephen Hawking, together with Roger Penrose, when they proved the singularity theorems, I think that really made it very clear that, in fact, this notion of an initial, or how should I say, a moment when the density had to have been extremely high, when Einstein's theory of general relativity ought to have broken down. I think these theorems were really instrumental. And
well, they were, and I lived through that phase.
yes,
and I think it's sort of obvious to everybody. If you have an exactly spherical object and shrink it down to zero radius, that will be infinite density, and we call that a singularity. And so people thought, well, if you just sort of change the symmetry a bit, and we're now thinking backwards in time towards the Big Bang, the different bits of the universe will sort of miss each other and go through and come out the other side. And what Penrose and Hawking proved is that you must have a singularity of some sort in the past, but it's not clear that all of the matter would hit it. It's just that you don't solve the problem of singularities, or which are really like boundaries or edges of space-time, by departures from homogeneity. And so there's still a bit of an issue there. Well, I think a huge issue. But there's of course a big issue if we say, well, the Big Bang was just the beginning of this particular cosmic phase. What preceded it, and then of course, do you go back forever and ever? And there are deep problems about an infinitely old universe as well, having to do with the laws of thermodynamics. And so we don't solve the problem of the origin of the universe by pushing it off or back to minus infinity. You still want to know why the universe is here, why it is like it is, and not like something else.
So, just to summarize this discussion about singularities, what we're saying here, I believe, is that initially, when the theory predicted that it would break down at a certain moment in time, that was a result of solving equations, which could only really be solved if we made the simplifying assumption that the universe was homogeneous and isotropic. We needed to do that just to make the equations tractable and solvable. And what Hawking and Penrose showed, and so there was a question about whether the singularities was really there, or was just an artifact of this highly simplified assumption that we're making. I think what you're saying is that the singularity theorems, when established, that the Hawking and Penrose singularity theorems established that no, there really is a singularity, no matter how, it's just unavoidable, no matter how you. So no matter, even if you go away from there's something similar, I think, for black holes. There's a similar kind of statements about.
But if I could add that, yeah, indeed, I think that's a nice segue to the fact that underlying these theorems are assumptions about the matter content and how matter behaves. And if it's just ordinary matter and ordinary radiation, then the theorem follows. However, there are more exotic forms of matter energy that actually evade the theorem, in which you can have, in fact, a smooth a bounce from previous contraction to expansion. And that's maybe at some point we touch upon that.
Right.
I don't want to overstep the moderator, but
well, let's get to alternatives to the Big Bang. But before we do that, I still want to say a few more things.
Okay.
So how come? So of course, in Hubble discovered the expansion of that all of the galaxies seem to be going away from us. Why was that not enough to already say, well, look, everything is going away. Either we're in a very special spot, or it's going away from all points. That means that it's expanding.
So yeah, my understanding is, well, I think maybe I can give a bit of context, because I think Einstein played such an important role in establishing the cosmological model, because people know about the static universe of Einstein, right? He didn't have an expanding universe that he was proposing. And in part, it was basically from observations. There was no real need for a dynamic universe. Peculiar velocities were thought to be small. But where he played a huge role is, in fact, in the establishment of this idea that the universe is infinite and has matter out to very large distances. At the time, it was unclear whether we were part of an isolated island galaxy surrounded with nothingness, or whether there was some evidence for, I think, what people call nebulae, but it wasn't clear whether these were other galaxies or
okay.
and he just postulated, based on a theoretical idea, that there had to be other galaxies out there distributed homogeneously. And
So
now
you mean Hubble, or do you mean Einstein?
no,
Einstein.
Einstein. Yeah. So it was purely theoretical, and that turned out to be correct. Now, and then of course Hubble came along, and that's really when the notion of an expanding universe was established, to my knowledge. But part of the reason I mentioned this is why is it then that this notion of a Big Bang didn't come to be immediately accepted? And I think the idea of Fred Hoyle, and Paul should correct me here, but was that indeed in this steady state universe, things were not only everywhere the same in space, but also everywhere the same in time, so to speak. That there was no preferred time, since matter was being continuous. It was not a static universe, it was expanding, but it was stationary, it was steady state, continuously creating matter. So that's also quite an appealing idea in itself.
I think if you look at the sociology of this, so Lemaitre, as you pointed out, was really the early architect of taking the Big Bang idea seriously. But I don't think many astronomers in the 30s really thought you could take general relativity, which wasn't well tested anyway at the time, and really tell the whole story right back to the beginning, the origin of the whole universe. It seemed a huge stretch. So by the 1950s, it was already dubious, and in a sense, it was sort of up for grabs as to alternative ideas. And I think Fred was ill-disposed towards the Big Bang Theory because it seemed a bit biblical to him. He didn't like the idea that there would be some special creation event, and so he was trying to find an alternative to that. Well, that's a sort of a curious thing. And this is a commentary really on how science is done as a community. And we have all sorts of cultural baggage, and there are bandwagon effects. It's good to work on certain theories and not others. And he certainly was out on a limb. He did have devotees in the 50s and even in the late 60s, a sort of handful of people who really clung to those ideas. But really after the background heat radiation was discovered, it was very, very difficult to sustain anything remotely like the original steady state theory. And now nobody really talks about it.
Okay, I think we're ready to move on to what could have happened before the Big Bang, right? Want to go for it? Tell us why we are considering sort of alternatives, and what are the different possibilities?
Yeah, very good. So to set maybe the stage for, as this is something I've worked on, a theory of cosmology that would involve the universe existing before the Big Bang. And the motivation for this is to explain the present conditions in our universe. In fact, when we look at this cosmic microwave background radiation, first of all, it's incredibly isotropic. It looks the same in all directions in the sky. We see radiation coming at us in every direction with a temperature that is almost virtually the same, up to 1 part in 10 to the 5. Okay, so it is almost the same temperature, but there are small temperature anisotropies as we look across the sky. And in the history of the universe, these initial temperature differences across the universe, they correspond to different densities in the universe. And that in time is what leads, because of gravitational attraction, leads to eventually, regions that were slightly more dense become denser as gravitational attraction does its trick, eventually leading to the formation of galaxies. So as Paul alluded to earlier, there's a wealth of information encoded in the statistics of these temperature anisotropies in the cosmic microwave background.
Right.
And there's good evidence that the origin of these temperature anisotropies were not set in the late universe by some right. It's really something that was imprinted or originates in the very early universe. Now, the leading or a candidate theory for the origin of these temperature anisotropies is cosmic inflation. The idea that shortly after this Big Bang, the universe underwent this very rapid exponential expansion of space. And for various reasons that we can get into, inflation does account for these anisotropies. But what motivated us is perhaps that they could be really a product of a previous phase, a contracting phase before the Big Bang. And that's what we set out to do. That was myself and Paul Steinhardt, Neil Turok, and Bert Overt in the early 2000s. Yeah, so that's a short story of what motivated this picture. Maybe one thing I can just briefly add, if I just to tell you this whole story, is that the other motivation at the time was really coming from developments in string theory. That there was a feeling that much like in the early 80s and 70s, when people had started to use the tools of quantum field theory to apply this to cosmology, such as Paul, and discovered all kinds of interesting effects, particle creation, etc., that perhaps now string theory was presenting us with a new toolbox, and maybe it could lead to similarly novel ideas. And that was the excitement that we had at the time.
So just to let our viewers know, Justin is speaking very modestly about his about a great discovery that he and his co-authors made, which is now thousands of citations, and it's called the ekpyrotic universe, and it was with Neil Turok and Bert Overt and Paul Steinhardt. You're going to be telling us a little bit more about that. But so what is the main ingredient? It was D brains, right, or brains in general?
Yeah. So this is the idea. Right. So in string theory, there are these objects that are membranes, higher dimensional membranes, which were really started to be understood within string theory in the mid-90s. And shortly thereafter, people started to think about the real possibility that perhaps our three-dimensional spatial universe might actually be a brain, which would have three dimensions in extent, spatial dimensions in extent, and the extra dimensions of string theory would be orthogonal to it. And so that picture, first of all, leads you to the idea that if we are on this brain, perhaps we could be moving around in these extra dimensions. This brain can be traveling. And the other natural possibility is that there can be other such membranes across the extra dimensions. In fact, that was one of the concrete scenarios that we were looking at the time. And so the idea that originated, or the sort of the beginning idea here, is that we would be living on a brain. We are living on this brain, and well before what we would think of as the Big Bang, there's a second brain some distance away, and these two brains are slowly attracted to one another. And eventually they collide. And when they collide, as most collisions, these collisions will be inelastic, resulting in the production of heat and matter. So we thought that was a picture of what a Big Bang would look like for an observer that is confined to this three-dimensional membrane.
So the new ingredient here is not only these brains, but the use of an extra dimension of space.
That's exactly right.
And so you're saying that we are on this hypersurface, on this three-dimensional world that we've seen.
Yes,
we're sort of stuck like flies to flies paper on a three-dimensional surface, which is separated in an extra dimension that we can't point to from another universe that's also there. And when the two of them collide, from our point of view, that looks like and then what happens? They collide again and again.
They may, then there is the possibility that this could happen. Maybe it just happened once, right? Or it may be the case that it happened periodically. So later on, Paul and Neil came up with this notion of a cyclic version of this scenario.
Can I ask you though, Justin, because I alluded earlier to problems with thermodynamics.
Yes.
If you go on like this, forever and ever, you might expect that the total entropy would keep going up and up and up. It was always a problem about the universe of infinite age. Einstein evidently didn't realize that you can't have a static universe with the stars shining forever and ever.
Olber's paradox. Yes.
Thermodynamically impossible. So how do you get around that problem?
That's a great question. So, okay, so now to go a little bit in the details of how this cyclical picture occurs. So as you said, right, just to set the stage, this notion that the universe may have gone through many cycles of expansion and contraction is an idea that goes back, I think, to the 30s. And it was Tolman who realized that if you take into account the second law of thermodynamics, the fact that entropy must increase in time, that in fact the size of each universe as you go back in time, each of these cycles corresponds to a universe that is smaller and smaller and smaller till it's a point. So you haven't really extended time to infinity in doing so. So the trick here, or the idea that to make this a cyclic universe is, if you think about the current cycle that we're in, we are now, the universe is currently accelerating because of dark energy. And this dark energy plays an important role in that picture, namely that it dilutes all the matter, all the galaxies. It must last long enough to smooth out the universe, getting rid of all this entropy. But it's not a dark energy that goes on forever. At some point, it's a dynamical form of dark energy, and it eventually leads to a new contracting phase such that these membranes will then come together again and again. So it's a story. It's a long story. It's a technical story that that was the idea to get around this thermodynamic objection.
And what happens to any black holes that are stuck like flies and flypaper to these brains, and that
they get spread out? So if you think about, they would also get spread out. So if you if we think about this membrane, all that from our vantage point, everything is being spread out, in the process.
But thermodynamically, the entropy, the total entropy has to go up. But if the total entropy is infinite, there's no problem with it. I mean, it doesn't have to go up in every little region, right? I can clean up my room and the entropy can go down locally without having, as long as it goes up more somewhere else. So in the case of, if the total entropy is infinite, then there's no problem with it. It can become more infinite, so to speak. Right? Is there really a problem with the second law?
Yes, and you mentioned dark energy. Others out there, maybe a few words explaining what that is, because that is, I think, new to the discussion today. Do you want to say something about it, or shall I?
Sure. I mean, as you want. Yes.
Well, Justin, you mentioned earlier about the gravitation between the galaxies, and most people think of gravitation as a pulling force, a force of attraction, and indeed, when I was a student, everybody assumed that the expansion of the universe was slowing and slowing because of this mutual gravitational attraction between the galaxies. Then in the late 1980s was discovered, somewhat to astronomers' consternation, that the rate of expansion is actually speeding up. Why is that? Well, one simple idea goes back to Einstein in 1917, I think, introduced what amounts to an anti-gravity force, a force of cosmic repulsion, and it's none other than the energy of empty space. If you take a volume, no matter there, you just take a volume of space, how do we know that's got zero energy? Zero seems like a good number, but you can't be sure because space is everywhere. So you can't isolate a chunk of space and put it on the scales and weigh it. So it's always possible that that empty space itself has energy. And it turns out, You might think, well, energy equals mc squared. That would just contribute to more gravitation, more pulling. But it turns out that to do this properly in physics, you have to have a pressure as well as an energy. And that pressure turns out to be negative to respect the symmetries of space-time. And negative, in general relativity, pressure is also a source of gravitation. And negative pressure means it anti-gravitates. So empty space in this theory, with this non-zero vacuum energy, just becomes self-repulsive. It just expands itself even with no matter around. And the belief is that either what I've just described or some other field that sort of mimics it is responsible for this accelerating expansion. We call it dark energy because we can't see it and we don't know what it is. That's my little 2-minute introduction.
Well, I think we're approaching the part of the Thinking Beyond webinar where we take audience questions. Before we do that, maybe do you want to just say some final words about sort of what are the ongoing issues or questions about this model, let's say, of the universe's
I just briefly, I think the biggest open question is really whether indeed one can bounce from a contracting universe to an expanding universe. I think if we had and part of the reason why that's an open question is that we don't have a rigorous realization of this in a model that like string theory where we can trust everything. And usually one can write down theories, but it's an exotic form of matter that has to be introduced, and there are debates as to whether these forms of matter really are legitimate to be considered. I think if one had I think it would be quite a moment. I think if one could prove that a bounce rigorously can be achieved.
I mean, don't you still have singularities on the brain at the moment of the impact?
Yeah, which is what indeed you have to resolve, and that and people had, if you take the limit where these brains are static, then perhaps something can be said, but the moment that they have a velocity and they collide, I think it's a very so that I think is the biggest question. There's this theoretical question that remains to be addressed. Other possibilities, as Paul mentioned, is that this singularity really is to be thought of as a quantum process, not so I think these are very interesting questions, exciting to explore.
There's another conceptual question, which I had a quick look at the Q&A from Cymbeline about the tablecloth. And of course, this comes up again and again, all real tablecloths have edges. How do we know it's infinite? And at the moment, we can't tell. But again, when I was a student, it was entirely possible that the universe was curved in on itself and was actually finite. Finite, not like a tablecloth having an edge, but finite like the surface of the Earth. You don't fall off it anywhere, but it wraps around and joins up with itself so that it's got no boundary, but it's a finite volume of space. And that's entirely fine in general relativity. We teach students how to describe such a universe. And then the question is, how would we know whether we're living in a universe like that? And you can know because if you count galaxies in a volume of space, bigger and bigger volumes, the numbers that you get, if it's the universe isn't spatially infinite, it would show up in those numbers. But unfortunately, to the best of our knowledge, if the tablecloth, is a big sort of hypersphere, it's enormously big, and we can't tell the difference between that and it going on forever. And we may never know whether it is or it isn't.
It's like those old video games where you walk off one edge of the screen and you come back from the other side. Anyway, speaking of galaxies, by the way, you said that I found it very interesting that you said that we didn't even know that there were more than one galaxy at the time that we detected the expansion of. How many galaxies are there currently in the known Hubble in the volume in a observable universe? you think it's
So in our observable universe,
staggering numbers?
it's a staggering number, right? 10 billion, something I've estimated, if I'm not mistaken. So our let's see. So we in a massive galaxy cluster, which are pretty rare, but nonetheless, there can be 10 to the 15 solar masses in such a cluster. Our own galaxy is 10 to the 10 solar masses. So
Right.
in a galaxy cluster, the amount of mass there is
100,000 galaxies in a
100,000.
single galaxy.
Yeah, so most of it is actually gas, so it's maybe more closer to 1,000. Most of the mass is in gas, but that's just in galaxy clusters. The total mass of the universe, yeah, is just a stupendous number.
And then people like to say, well, how many stars? So if you add those up, it's about 10 to the 20, or maybe a little bit more than that, and more than grains of sand on the seashore, as people often say.
I think we have about 200 billion stars in the Milky Way, which is one galaxy out of.
And people say, oh, the universe is so big, there has to be life out there somewhere. A ridiculous argument, in my view, but for another day, not for this.
All right, let's get to the questions.
Yes.
We have a lot of questions. Okay. Oh, this is a good one. This is Mark Wagner saying, how is dark energy different from the ether that was proposed to explain how gravity acted at a distance?
Yeah, that's a great question. Well, it is similar to the ether in the sense that it is a form of energy that pervades all of space. The simplest form of dark energy, as Paul was alluding to, is simply a cosmological constant, the energy of the quantum vacuum. And that is everywhere in space, and it is constant in time, that form of energy density, I should say. Yeah, but of course it plays a very different role than the ether that eventually was discarded thanks to special relativity, in that it doesn't provide a medium for light to propagate or anything like that, but it is simply a allowed form of energy allowed by Einstein's theory of general relativity, which if it weren't for gravity, we would be oblivious to that energy density, because we can always shift, as we know from freshman mechanics, you can always shift the energy by a constant, but somehow gravity cares about that overall constant.
And we should point out that there's not very much of it. I worked out that it takes, I think, 1 million cubic kilometers of dark energy to boil a kettle.
Yeah, I think it's about the energy of 1 atom per cubic meter or something like that, right?
Yeah.
That's, yeah. Okay, so here's another question from Cymbeline. How do we know that the tablecloth is infinite? We sort of got to this. If it isn't, would the expansion cause the edge of the tablecloth to get punched up? So I think we know that there's no edge. Or are there scenarios
that's
where
a very interesting. That's a very interesting question, because it even depends on how we go about going to that edge, right? So I don't know if we want to go, but it's fun to think about. So why don't we go there, right?
Sure.
So indeed, in cosmic inflation that we were discussing earlier, there is this idea in eternal inflation, where inflation may not be going on anymore in our local region of the universe, but elsewhere in this multiverse, right? In that picture, our universe may be a bubble that was formed, that was nucleated in this eternally inflating space-time. And that's a very subtle question now about what constitutes the edge of space, because we are within a bubble. So there is an edge, there is a wall to our bubble. But when we think about describing the interior of that bubble as we would in a cosmological sense, that is to say, thinking about surfaces of constant time, simultaneous surfaces of simultaneity that are compatible with cosmology, those are actually infinite. So that's a mind-boggling thing to think about, but if you just keep on going in the usual way you would do, if you could really go out in space, you would find that you're part of an actual infinite surface of simultaneity, even though you are part of a bubble whose walls in some other sense is a finite distance away. Anyways, I just wanted to throw out there just because it's fun to think about.
And this bubble is stupendously big. So it's a very,
It's stupendously big indeed. Yes, that's right. And in fact, hitting the wall of the bubble is really like going back in time, because that bubble wall, for in all intents and purposes, is the Big Bang from our point of view. So it's also,
and of course, there are these ideas that if there are multiple bubbles, they could have collided.
They could collide, and if they did, and we saw observational evidence for this, then that would be, I think, quite a direct way to at least infer the existence of these other bubble universes, which would be quite fascinating. Yeah,
it's fantastic, because we sometimes think that a multiverse is simply an abstract idea that's untestable. I mean,
yes,
it doesn't have to be untestable. It probably
Indeed.
is, but there could be some effects that like that, where two universes collided.
Well, so the simplest idea is the bubbles are expanding as the universe expands, but they're moving apart from each other faster than they're expanding. And so they won't collide in those circumstances, but there are other scenarios where they do collide, or where one bubble could nucleate inside another. I mean, you basically can have what you want.
So here's a question for you, Paul, actually. It says, can you elaborate on your view that related to whether or not the size of the universe indicates that life must be out there?
Well, yes, we can deal with this topic properly in some other time. But the big problem about the origin of life is, how did non-life turn into life? How did a mishmash of chemicals turn into a genuine living thing? And the answer is we don't know. Presumably there was a chemical pathway from simple building blocks to something truly living. That might have been quite a long pathway, and it might have had many difficult steps to overcome. And people think, well, with so many planets, there might be like 10 to the 23 planets within the volume of the universe we can actually observe, surely it's going to happen in many places. But that number, 10 to the 23, it sounds like a big number. But if you start putting in probabilities that this chemical reaction might occur on a planet over 1 billion years, with a probability of 1 in 1,000, and then the second one, 1 in a million, and you have to multiply all those probabilities together, you can get numbers that blow 10 to the 23 out of the water, and then you would conclude that it's happened only once in this volume, and it's no surprise that we're witnessing that, because it has to be us. And now, if you take this bigger view, you imagine that we're now not talking just about the Hubble volume, the universe that we can actually observe, but the big bubble we were just discussing. Then sure, on that sort of exponentially bigger scale, we would expect that even these highly improbable sequences of events would have occurred again. But just within the volume we can observe, it's easy to convince yourself that the probability of life happening twice could be extremely low. We might be the only ones here. Now, of course, we don't know, because we don't know what the process was. So it's simply my feeling is, well, we should go look for it and try to answer the question that way. But it could be a very, very improbable sequence of chemicals.
So here's a question from Jonathan Durkin, who's at the School of Earth and Space Exploration at ASU. If we were in a significantly less dense part of the universe, would we have come up with a different age of the universe?
Oh, that's a very interesting question. Yes, in fact, right. So one way we infer the age of the universe, or one ingredient in this, is the current rate of expansion of our universe, what we call the Hubble constant. And indeed, one can always wonder, are we in a special place, perhaps an underdense region, such that our measurement of the Hubble constant is not representative of what the expansion rate is on larger distances? And so it's something that we can try to model. To what extent, how special would we have to be, and also how close to the center would we have to be of that underdense region? Because after all, the expansion of the universe does look isotropic, looks the same in all directions to a good approximation. And it's interesting you asked that question because that's something that people have actually played with or thought about theoretically, because now there's some discrepancy that is discussed often in precisely the value of the Hubble constant at the level of, I mean, it's not a huge difference, 5% or so, but between different observations. So it's something that people have thought about, whether we are perhaps in a special place of the universe. And as far as I know, that idea doesn't quite work, but it's a very interesting question you asked.
It's a 5% discrepancy that just hasn't gone away.
Exactly. Yeah.
Yeah.
It's a persistent discrepancy. Yeah.
So another question, just to clarify. So the light of the observable universe that we see is what defines what we mean by observable, right?
That's right. That's exactly right. Yeah. So the observable universe is in principle we only see a portion of what the universe is, and that's defined by the furthest distance that light has had time to travel.
Yeah.
Since the Big Bang, or more since the microwave background, to be precise.
Although, to be fair, there's a barrier to how far we can actually see with light, because of at some point the universe became opaque.
Right. That's what I meant. So yeah, exactly. So with light, you can only go as far back as the cosmic microwave background, indeed, because the universe became opaque. If one day we could do neutrino, we could discover the cosmic neutrino background, then that would bring us even further back in time.
Or the gravitons.
Pardon me?
Or the gravitons.
Or gravitational waves. Yeah, I was going to say that would be the ultimate. That would, in principle, could take us all the way indeed to the Big Bang, in hypothetically fantasizing. But yeah,
This is a finite volume, and when we talk about the universe, it's a confusing term, because sometimes we mean what everything is there. Sometimes we mean what can, in principle, be accessed with the best instruments we can imagine, and that's a finite volume.
That's right.
So we don't know that the actual universe is infinite or finite. We do not, but of course our observable universe is finite, because there's a finite amount of time has passed. Right. So let's see. One more question. Do we have time? Okay. Well,
we might get through too.
1 second. Let's pick. Oh, so Phil T asks if in some sense the laws, we're going to get into this kind of questions at the end, the laws of physics transcend the universe, encoding all the information of how the universe works. Where was that information that the laws of physics represent? So do we have an idea that information must exist in space and time, or how does, in other words, where were they written down?
Yes, so are the laws of physics in some transcendent realm beyond space and time, like some mathematicians think of mathematics, a scholar called Platonism after Plato, that it's these mathematical truths are true whether there's a universe or not. Do we dignify the laws of physics with that? Are they somehow the basement reality on which the whole of existence depends, or are they the inventions of physicists? A whole different point of view. This is a cultural thing, and the laws of physics are just conveniences that we apply to make sense of the universe and make our lives easier, win Nobel Prizes and so on, but they don't really exist. And we don't have a trained philosopher, I think, among us who could tell me that I don't know what I'm talking about.
I think it's a profound question why, in fact, just physics is well described by mathematics, why the universe evolves according to mathematical rules. That also, I think, to me, is a profound question. Why well defined.
This is I've often wondered about that, right? About the unreasonable effectiveness of mathematics. Okay. For our last and final question.
But didn't you have one by email as well? Are you looking only at
well, we covered that actually.
Oh, okay. We did. Okay.
So if the name of the Big Bang is so misleading, can we come up with a new name that appeals to kids and people who aren't physicists? What would you say?
Yeah, let's come up with one now. Agree on it, and it's settled.
Well, actually, I'm reminded of a Calvin and Hobbes cartoon in which Calvin, I think, complains that the Big Bang is such a lame name, and he proposes that so his pet tiger Hobbes asks him, "What would you call the creation of the universe?" And he says, "The horrendous space kablooey."
Perfect.
He then goes on to say that Tyrannosaurus should be changed to monstrous killer death lizard. All right, on that note.
Why don't we say anybody out there who thinks they have got a better name, they should just email it and we'll announce it at the next Thinking Beyond.
Right. Okay, well, we're out of time. Thank you so much, Justin. That was a great, it was always wonderful to talk to you. And thank you everyone for being here. And see you at next month's Thinking Beyond.
Thanks very much. That was great fun. Bye.
Bye.